Hello and welcome to today's lesson on nuclear fission, which is part of the atomic structure topic in GCSE Separate Science Physics. So in today's lesson we're going to look at understanding the process of nuclear fission. So if we've been successful and learned in today's lesson, we should be able to describe what the process of nuclear fission is, construct a chain reaction diagram based on nuclear fission, and understand how nuclear fission can release energy, which links to the following part of the GCSE Separate Science Physics specification 4.4.4.1 nuclear fission, which is separate science only content. Now in previous lessons we've looked at how unstable nuclei can turn into more stable nuclei. Now this process is called radioactive decay, and eventually all unstable nuclei will decay into stable nuclei. Now when this happens, the unstable nucleus will emit either alpha, beta and or gamma radiation, and this radiation comes from the nucleus. However, there are two other processes which an unstable nucleus can carry out to increase its nuclear stability. Now the first process is when an unstable nucleus can split into two smaller, more stable nuclei. Now this only happens in larger unstable nuclei, elements larger than iron. Now this process is called nuclear fission. Now nuclear fission is the mechanism behind how nuclear bombs and nuclear power stations work. Now controlled nuclear fission is found in nuclear power stations, whilst uncontrolled nuclear fission is found in nuclear weapons. Now the other process which increases nuclear stability is called nuclear fusion, which we'll look at in upcoming lessons. Now nuclear fusion takes place in stars like the sun. So all nuclear processes increase the stability of the nuclei involved. It is the aim of all nuclear decay processes to increase the nuclear stability. So what this means is, if you look at this diagram, every element above iron can increase its stability by carrying out fission. So the fission process for any nucleus above iron will increase the stability of the nucleus, whilst any element below iron will carry out fusion, as fusion will increase the stability of that nucleus. Now fusion can actually have a more stabilizing effect than fission, which is why it can take place in places like the sun and release a lot more energy than when fission is carried out in a nuclear power station. Now iron is the most stable nucleus in the universe, and this is due to its configuration of protons and neutrons. Iron will not carry out fission or fusion, so fission or fusion would stop if the nucleus becomes iron. So stars actually stop giving out energy via fusion when they start to produce iron in their core. So this graph here illustrates the nuclear fusion and nuclear fission ideas. Every element above iron can carry out fission, and every element below iron can carry out fusion. Now the nuclear fission process is determined by the subatomic particle, the neutron. Now let's start us off by considering one unstable uranium nucleus. Now uranium is considered unstable as it's the largest natural element. It is the furthest possible element away from iron. So what we need to do with our unstable uranium nucleus is we fire a neutron into this uranium nucleus. So this uranium-235 is an unstable nucleus. You fire a neutron at it, it absorbs this neutron and it makes the nucleus even more unstable. So it becomes uranium-236 and it's now extremely unstable. And at this point this will actually split into two more stable smaller nuclei, either barium or krypton. Now fission caused by a neutron being absorbed by the nucleus is called induced fission. Now fission which occurs naturally is called spontaneous fission, which is very rare. So there's actually two types of fission: induced, which is caused by a neutron being absorbed by a nucleus, and spontaneous, which is when a nucleus just by itself decides to split into two. Now the nuclear fission process increases the nuclear stability. So what happens is our uranium-235 is very unstable. It then carries out fission and it produces barium and krypton, which are two more stable nuclei. Now it's also important to note that during the fission process the total mass before is greater than the total mass after. Now where does some of the mass go? Well, that mass is turned into energy and is also released in the fission process. So this is why the fission process can produce a lot of energy. Per kilogram there's 1,000 times more energy via nuclear fission than by burning, combusting coal, oil or gas. So when you have your fission process taking place, energy is released in this process, and this energy is produced due to the mass from the original uranium turning into energy. Now this links into energy conservation, as the full rule of energy conservation is that mass and energy together cannot be created or destroyed, only transferred. So some of the mass of the unstable nucleus has turned into pure energy. Now this energy can be found as the kinetic energy store of the products. So what that means is all products of the nuclear fission process will have kinetic energy. So that's one way in which energy is released. Energy can also be released as gamma rays. So some gamma rays can also be produced in the fission process to carry this energy away. Now, very importantly, as well as gamma rays and krypton and barium, you also produce 3 neutrons in the fission process. Now, these neutrons come from the remains of the large unstable uranium nucleus, and the neutrons, the krypton and the barium all have kinetic energy. Now, it's very, very important of what's going on in our fission process. So before fission, you start with an unstable uranium nucleus and a neutron, and after fission, you have 2 smaller, more stable nuclei, 3 neutrons and some gamma rays. So, and remember what we said, all the products of nuclear fission have kinetic energy. Now it's important that 3 neutrons are made in this fission process, because these neutrons go on and fission other uranium nuclei. So this continues the fission process with other uranium nuclei, which causes the process to continue without you having to place further neutrons into the actual reaction into the chamber. Now this idea is links the process together. So because the previous fission event links to the next fission event like a chain, this is why nuclear fission is called a chain reaction. Each reaction links to each other like links in the chain. So we can look at this with the following diagram. You start off with a neutron that gets fired and absorbed by an unstable uranium nucleus. It makes it even more unstable and makes it want to split into 2, and when it splits into 2, you have your new, more stable nuclei. That then produces some energy, which can be either in the form of kinetic energy or gamma rays, and it will also produce 3 more neutrons, which can then go and find new uranium nuclei. Now a previous fission event can cause more fission events. The fission events are linked together in a chain. Now each fission event releases energy, which means there's a constant release of energy in the fission process. Now each fission reaction releases neutrons that are used in further reactions, and you get more and more and more energy released. Now each event releases energy due to mass changing into energy. Now as you'll notice, as the fission process continues, there's more and more and more fission events every second. This means more and more and more energy is released every second in the fission chamber. So a chain reaction will produce more and more energy at each stage. So an increasing amount of energy is released at each stage. Now the number of neutrons fissioning uranium increases exponentially. Now we call this idea an uncontrolled chain reaction. Now the technical term for this is we say the reaction has gone supercritical. Now this can actually cause a nuclear meltdown in a nuclear power station, which is when so much energy is released the uranium fuel actually melts. Now this links because one fission event each produces 3 neutrons. So if 3 neutrons is produced each time a uranium nucleus splits, one fission event leads to 3, which leads to 9, which leads to 27, leads to 81, to 243, so on, so on, so on. But you can see more and more fission events are happening every second. Now this is called uncontrolled, as we're doing nothing to control the neutrons being released. Now eventually, an uncontrolled chain reaction increases the energy released as the fission process goes on. Eventually, there's a great amount of energy all released at one time. This will eventually cause an explosion, and this is the process behind a nuclear weapon. So each fission event releases neutrons that are used in further events. This releases more and more energy at each stage if the chain reaction is not controlled. So if we let the chain reaction go on and on and on, more fission events will happen done at once, this releases more and more energy simultaneously. This will eventually cause a massive explosion, which is a nuclear weapon. So if we want to harness nuclear fission in a power station, we don't want this to occur, so we've got to control the chain reaction. So remember, an uncontrolled chain reaction leads to a nuclear weapon or a nuclear bomb, and because the amount of energy released per second increases as the chain reaction goes on. The chain reaction is uncontrolled. Now again, we can also call this supercritical. Now we've got to control the chain reaction by ensuring the number of neutrons fission in uranium stays consistent or constant. Now we call this a controlled chain reaction. Now the technical term for this reaction is that this reaction has gone critical. Now this can produce a constant power output. So what happens is the amount of energy released per second stays the same as the chain reaction goes on. The chain reaction is controlled. So the chain reaction is controlled in a nuclear reactor to control the amount of energy released, because if the chain reaction becomes uncontrolled in a nuclear reactor, this can cause too much energy to be released at once and cause an explosion. Now the chain reaction is controlled by absorbing neutrons at each stage of the process, because if the chain reaction becomes uncontrolled, it can cause too much energy to be released at once, and that can cause an explosion, which is what had happened at the Chernobyl nuclear power station in 1986. Now carrying out the process of nuclear fission and nuclear fusion releases energy which can be used in power stations to heat up water into steam and in nuclear weapons. Now this is why nuclear fission and nuclear fusion release energy, and it's due to the most famous equation in physics history. It's due to the concept that mass and energy can be converted from one form to another, because Albert Einstein realized that mass was just another form of stored energy. In fact, mass is the most compressed store of potential energy. So he linked the two and said they were equivalent, which is the equation E equals mc squared. Now technically, it's not total energy, because the total energy must be the same before as after. It's the total mass slash energy must be the same before as it is after. Energy slash mass cannot be created, it cannot be destroyed. So this means that in the fission process, the total mass before is larger than the total mass after the fission process. Now the difference between the two masses is the difference in the energies, and the energy is then released in this process. So the amount of energy produced from the missing mass can be calculated using the most famous equation in physics, because the total mass energy before equals the total mass energy afterwards, and they are linked with the equation. The energy released in the particular process is equal to the missing mass, the mass that has been changed between before the process and after the process, times by the speed of light squared. This means energy and mass can change between the two forms. So we can say delta E, or triangle E, is equal to delta or triangle M times by c squared. Now we know that the speed of light, or c squared, is 3 times 10 to the 8, so that is actually a very large number. So to clarify, E equals mc squared links energy and mass together. Mass can be considered a store of potential energy. In nuclear fission, some of the mass of the nuclei in the reaction is changed to energy, so the overall mass after the fission process is slightly less than the overall mass before. This then is turned into energy and given out is predominantly kinetic energy, and we can calculate the amount of energy given out by saying the energy released, or delta E, is equal to the mass that has changed, the missing mass, delta M, times by the speed of light squared. And because the speed of light is 3 times 10 to the 8 meters per second, this means a little amount of mass can be transformed into a lot of energy. So what have we learned in today's lesson? Nuclear fission is the splitting of a large and unstable nucleus, for example uranium or plutonium. Spontaneous fission is rare. Usually for fission to occur, the unstable nucleus must first absorb a neutron. The nucleus undergoes fission by splitting into two smaller nuclei roughly equal in size and emitting 2 or 3 neutrons plus gamma rays. Energy is released by the fission reaction. All of the fission products have a kinetic energy, and the neutrons may go on to start a chain reaction. The chain reaction reaction is controlled in a nuclear reactor to control the energy released, the explosion caused by a nuclear weapon is caused by an uncontrolled chain reaction, and you should be able to draw and interpret diagrams representing nuclear fission and how a chain reaction may occur. So if we've been successful and learnt in today's lesson, we can describe what the process of nuclear fission is. We can construct a chain reaction diagram based on nuclear fission. We can understand how nuclear fission can release energy. I hope you've enjoyed today's lesson on nuclear fission, which is part of the atomic structure topic in GCSE Separate Science Physics. Thank you very much for watching this video and have a lovely day.